Welcome to ArXiv Preprint Server Daily, AI Frontiers. Today we're exploring cutting-edge research in computer vision based on papers published on April 28, 2025. This episode synthesizes key themes, methodologies, and breakthroughs across 18 recent papers, providing a comprehensive analysis of where computer vision research stands today. We'll examine dominant research directions, analyze groundbreaking results, explore common technical approaches, and take a deep dive into three particularly influential papers that exemplify the current state of the field. Computer vision sits at the intersection of artificial intelligence, mathematics, and engineering, with the fundamental goal of enabling machines to derive meaningful information from visual data. This capability underpins countless applications we now take for granted, from facial recognition on smartphones to autonomous navigation systems in vehicles, from medical image analysis to augmented reality experiences. Despite the ease with which humans process visual information, replicating this ability in machines presents profound challenges. Visual data contains rich information about objects, scenes, spatial relationships, and lighting conditions that requires sophisticated algorithms to interpret accurately. Recent years have seen remarkable progress in computer vision, driven largely by advances in deep learning, the availability of large-scale datasets, and increasing computational power. The first major research theme we've identified is 3D understanding and reconstruction, converting 2D visual data into meaningful 3D representations. Pataki and colleagues present MPS-FM, a novel approach that enhances structure from motion with monocular depth and normal priors. Their method enables reliable 3D reconstruction under challenging conditions where traditional approaches often fail, such as scenes with low overlap or high symmetry. Lee and team introduce LIRM, a large inverse rendering model that can rapidly reconstruct high-quality 3D content including shape, materials, and view-dependent effects from sparse views. Sawada and colleagues present FreeBIS, a frequency-based approach to neural implicit surface representation. This focus on 3D understanding has growing importance for applications in autonomous driving and augmented reality, with particular emphasis on reliability under challenging real-world conditions. The second prominent theme revolves around diffusion models and generative AI. These approaches have revolutionized image generation and are now being applied to increasingly sophisticated tasks. Wang and colleagues present integration flow models, which address limitations in ordinary differential equation-based generative approaches to improve sample quality while maintaining computational efficiency. Saito and team explore Riemannian metrics for diffusion models, treating the data space as a Riemannian manifold to enable more realistic image interpolations. Kamirul and colleagues apply physics-informed diffusion models to SAR-ship weight generation from text prompts. We're seeing a clear trend toward reducing computational requirements while maintaining high-quality outputs, and increasing application of these techniques to specialized domains beyond general image synthesis. The third major theme focuses on multimodal learning and vision language models. Researchers are increasingly developing systems that can process and relate information across different types of data. Ma and colleagues introduce Spatial Reasoner, a large vision language model that addresses 3D spatial reasoning with explicit 3D representations. Zhang and team propose focus-centric visual chains to enhance vision language models' ability to handle complex multi-image inputs. Kui and colleagues develop a transformer-based fusion approach that combines visual and wireless signals for crowd-counting applications. These approaches demonstrate how combining information from different modalities can lead to more robust and comprehensive understanding of complex scenes. The field is clearly moving toward integrating multiple data streams to achieve more human-like understanding of visual environments. Domain-specific applications constitute another significant theme across the papers. In remote sensing, Guo and colleagues introduce Deep Andes, a self-supervised vision foundation model for multispectral satellite imagery analysis in Andean archaeology, while Palushko and team explore augmentation strategies for flood detection using remote sensing imagery. Medical imaging applications are represented by Cherikara and team's Dynamic Contextual Attention Network for endoscopic polyp diagnosis and Yavari and colleagues' work on incremental learning for prostate cancer detection. Aerial applications include TAC and colleagues' improvements to trajectory continuity in drone-based crowd monitoring and Yi and team's CO drone benchmark for oriented object detection in UAV scenarios. Agricultural monitoring is addressed in Callejeras and colleagues' work using Sentinel-2 satellite imagery to monitor digestate application. These papers demonstrate how computer vision techniques are being tailored to meet the specific requirements and constraints of diverse application domains. Several groundbreaking results stand out across the papers we've analyzed. Wang and colleagues achieve remarkable one-step image generation with their integration flow models, reporting Frechet inception distance scores of 2.86 on CIFAR10 and 4.09 on ImageNet. This represents a significant advancement in computational efficiency for generative models. Li and team's LIRM accomplishes sub-second 3D reconstruction including shape, materials, and view-dependent effects, a task that traditionally requires minutes or hours. Guo and colleagues demonstrate the effectiveness of self-supervised learning for specialized domains with their Deep Andes Foundation model for multispectral satellite imagery. Ma and colleagues show how explicit 3D representations can improve spatial reasoning capabilities in vision language models. Pataki and team achieve reliable 3D reconstruction in challenging environments where traditional approaches typically fail, using their MPS-FM approach with monocular priors. Across the papers, several methodological approaches recur, highlighting current trends in computer vision research. Diffusion models and flow-based generative approaches have emerged as a dominant paradigm in generative computer vision. Transformer architectures, originally developed for natural language processing, have been widely adopted and adapted for visual and multimodal processing tasks. Self-supervised learning approaches leverage in-labeled data to learn useful representations, as demonstrated in Guo and colleagues' Deep Andes model. Multimodal fusion techniques combine information across different input types to achieve more comprehensive understanding. Neural implicit representations encode 3D shapes or scenes as continuous functions represented by neural networks, offering advantages for modeling complex 3D structures with high fidelity while maintaining compact representations. Let's examine the first seminal paper in detail. Wang and colleagues introduce integration flow models, a groundbreaking approach to generative modeling that addresses fundamental limitations in ordinary differential equation-based generative models. Their primary innovation is directly learning the integral of ODE-based trajectory paths without solving the ODE functions. This approach sidesteps the discretization errors inherent in numerical ODE solving. The authors incorporate the target state as an anchor to guide reverse time dynamics, contributing to both stability and accuracy. Their model achieves remarkable one-step generation results, with FID scores of 2.86 on CIFAR10 and 4.09 on ImageNet. These results are especially impressive considering they are achieved with just a single network function evaluation. The ability to generate high-quality images in a single step has profound implications for applications requiring real-time generation, such as augmented reality and interactive systems, while significantly reducing computational resources and energy requirements. The second seminal paper comes from Li and colleagues, who present the Large Inverse Rendering Model, LIRM. This transformer-based architecture achieves high-quality reconstruction of 3D shape, materials, and view-dependent radiance fields in less than a second. While recent large reconstruction models have shown impressive results in sparse view reconstruction, they still struggle with accurately reconstructing unseen parts, capturing glossy appearance, and generating relightable 3D content. LIRM addresses these limitations through several key innovations. An update model for progressive refinement as new views become available, a hexaplane neural signed distance function representation for detailed textures and geometry, and a novel neural directional embedding mechanism to handle view-dependent effects. The model produces reconstructions with sharp textures, accurate geometry, and realistic material properties, including specular highlights and reflections, while requiring only a fraction of the inference time compared to optimization-based methods. This represents a major step toward making high-quality 3D reconstruction accessible for real-time applications. The third seminal paper comes from Ma and colleagues, who introduce Spatial Reasoner, a large vision language model designed specifically to address 3D spatial reasoning with explicit 3D representations. While recent approaches typically perform spatial reasoning implicitly, making it difficult to understand how models make decisions and limiting generalization to unseen question types, Spatial Reasoner employs a novel architecture that integrates explicit 3D representations across three key stages: perception, computation, and reasoning. In the perception stage, the model extracts 3D information from 2D images. The computation stage explicitly calculates spatial relationships between objects using their 3D coordinates and properties. In the reasoning stage, the model integrates these explicit spatial computations with a language model to answer questions about spatial relationships. The results demonstrate superior performance on spatial reasoning benchmarks and, crucially, better generalization to novel question types. This approach creates a coherent interface between visual perception and language-based reasoning, with significant implications for applications in robotics, autonomous navigation, and human-AI interaction. Looking at future directions in computer vision research, several promising paths emerge. We anticipate continued development of more efficient generative models, building on the success of approaches like integration flow models. The integration of physical principles and domain knowledge into computer vision models is likely to expand, potentially leading to models that require less data and generalize better to new scenarios. Further advances in multimodal learning will enable models to integrate information from diverse sources including images, video, text, audio, and sensor data. Specialized models for specific domains and applications will continue to proliferate, leveraging general advances in computer vision while adapting them to unique challenges in fields like healthcare, agriculture, and environmental monitoring. Finally, we expect increased focus on making advanced computer vision models more accessible, interpretable, and environmentally sustainable through more efficient architectures, better transfer learning techniques, and more transparent reasoning processes. In conclusion, the computer vision research landscape continues to evolve rapidly across multiple fronts. We're seeing remarkable progress in efficiency and quality, as demonstrated by Wang and colleagues' one-step image generation and Li and team's sub-second 3D reconstruction. The field is increasingly integrating multiple modalities and knowledge sources, as shown in Ma and colleagues' Spatial Reasoner and Zhang and team's focus-centric visual chains. Domain-specific applications are benefiting from specialized approaches, evident in Guo and colleagues' Deep Andes Foundation model and Cherukura and team's network for endoscopic polyp diagnosis. Despite this progress, significant challenges remain, including computational demands, data requirements, and evaluation complexity. Computer vision continues to advance fundamental capabilities while simultaneously expanding into new application domains and addressing practical constraints, demonstrating the field's vitality and potential to transform how machines perceive and understand the visual world. About this synthesis. This research analysis was created using AI tools, including content generation with Anthropic's Claude 3.7 Sonnet, text-to-speech synthesis from Google, and visual elements from Grok image generation. All generated content was reviewed by human experts for accuracy and relevance. This presentation is part of ongoing efforts to enhance research accessibility and knowledge sharing across the computer vision community. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from ArXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights.